Okay, hello guys. This day I'm going to continue talking about pressure build-up test. Last week or the week before, we have started talking about pressure build-up test. Now we know how to calculate the permeability from the pressure build-up test. We know how to calculate skin factor, and of course we know how to calculate wellbore storage factor from pressure buildup test. Last week I solved two examples about pressure buildup test using Horner plot where the time axis for the time for Horner plot is used as production time Tp plus delta T divided by delta T. We have solved the same example using delta TE. In this case, the time is used as Tp times delta T divided by Tb plus delta T. And the third approach for the pressure buildup is delta T as delta T. When the production time is really very short, then we may be able to use delta T as it is, without considering Tp. So this week we will talk about the how can we predict average reservoir pressure from pressure build-up test. So let me share with you the slides for this point. So here is chapter 1, and I'm going to go directly to the topic of average reservoir pressure from pressure build-up test. This would be somewhere here. Where is that? Yeah. Of course, one thing, last week I have talked about it also. Last week I talked about how to calculate the distance from the wellbore to a fault or to reservoir boundaries, how to calculate D. And we have solved example 161 and 162. Either, of course, how to calculate D using pressure drawdown test and the pressure build-up test. So here is what we need to cover it this week. Average reservoir pressure from pressure build-up test. For average reservoir pressure or initial reservoir pressure, sometimes we could say initial reservoir pressure, or we could say average reservoir pressure. Initial reservoir pressure, if we have really a new oil field and we do not have that much producing wells, so in this case, if we have shut-in wells, the pressure could increase and it could reach initial reservoir pressure. But if we have a mature oil field, very old oil field with a lot of producing oil, then the pressure in this case is going to increase to average reservoir pressure, not initial reservoir pressure. However, the pressure that we are going to have it from pressure build-up test, it is not going to be initial reservoir pressure. and it is not going to be average reservoir pressure. It is going to be some value, and we don't know what is this value, but we are expecting that this one could be either initial reservoir pressure or average reservoir pressure, and this one is called B star, because if we need to get back to initial reservoir pressure or average reservoir pressure, we have to shut in the well for a long time. Therefore, what we are going to do, we are going to have the uh, extrapolation. So is it going to be really average reservoir pressure? Of course, we don't know. But we are gonna be really very close to average reservoir pressure or initial reservoir pressure. This is why we would prefer to use B star instead of average reservoir pressure or initial reservoir pressure. B star could be close to one of them. Now, what are the techniques could be used for predicting average reservoir pressure, for calculating average reservoir pressure? We have the first one that is called MBH, Matthias Bruns Hasbrouck. This is the first one. Matthias Bruns Hasbrouck. The second one is Dietz method. Dietz method. The third one is Rami Cope method. The fourth one, MDH, Miller-Dice Hutchinson. So basically, we have four techniques to calculate average reservoir pressure. They are MPH, Matthias Bruns Hasbrouck, Dietz method, Rami Cope method, and MDH, Miller-Dice Hutchinson. And of course, we do have two more techniques, but they are not really uh, well known like the four. These two are external pressure method, external pressure method, and direct method. Direct method. So basically, we have four main techniques to calculate average reservoir pressure using a pressure build-up test, and we do have two other techniques. They are not very well known. The first one is the external pressure method, and the second one is the direct method. Let us start with the first one, that is MPH, or Matthias Bruns Hasbrouck. Using this technique, the MPH, we're going to go with the Horner plot first. So what we need to do now, we need to plot Horner plot. So what does it mean? We have to prepare the x-axis, the time axis, as Tp plus delta T divided by delta T. Okay? And of course, when we have this plot, we're going to calculate the permeability. And then we're going to calculate what skin factor, we're going to calculate wellbore storage. So we're going to do all things required by well test analysis. And then we need to calculate what is called TDA, the starting time of a pseudo steady state. The starting time and dimensionless for pseudo steady state. From where we can get TDPSS, or the starting time for pseudo steady state in dimensionless form. This could be taken from where? This could be taken from table 146. Let me get back to table 146 so we could know how to get TDPSS. This is TDPSS, see? So what we need to obtain TDPSS. This is TDPSS. Dimensionless time for the starting time, dimensionless time for the starting of a pseudo steady state. And this time is calculated based on the area of the reservoir. This is why it is written TDA. As you can see, it is written TDA. When we have TDA, this should be what? This should be the starting time, or this is the dimensionless time calculated based on the area of the reservoir. Why? Because, guys, at the beginning of my classes, I told you to memorize the definition of TD. What is the definition of TD? If you remember, the definition of TD, I'm going to put it here. The definition of TD, dimensionless time, is what? Point O 2637 K permeability times T, see, divided by what? Phi mu CT RW square. This is TD. Now TDA is what? TDA is the same exactly, but what we are gonna put here, we're gonna put what? Same point 0.00267 KT, see, phi mu CTA, see? So instead of RW, we're gonna put A. See what I'm saying? It's just like TD, and we're gonna multiply by A here, and divided by A, see? Then we're gonna put A here, and put RW there, see? This is what we can do. So basically, TD, dimensionless time, the one that we know, is TDA times what? Times A divided by RW square. See? Or TDA can be written as TD times what? RW square divided by A. See? RW square divided by A. Okay. So this just, it's not important now, but we need to talk about something like that. Okay. So now, going back to Matthias Braun's Hasbro, as I said, you're going to start with Horner plot, TB plus delta T divided by delta T, and you're going to plot the time versus pressure on semi-log plot. You will get a straight line, you will get the slope, and then from the slope, you are going to calculate the permeability. Then you are going to calculate skin factor, and you will be able to calculate wellbore storage. So you are done with this part. When you are done, then you need to calculate what? You need to calculate average reservoir pressure. For this case, what you need? You need to obtain what is called TDA for pseudo steady state. And this one is taken from what? From table 146. So let us move up and see where we can find table 146. So table 146, this is for what? If you remember, guys, when we have talked about the shape factor, this is table 146. See, here is table 146. Let me make it bigger a little bit so you could see that very well. This is table 146. If you look at this table here, see, what you are going to have, see, exact, see, this is what the one that we are looking for. See, this is the one that we are looking for, exact for TDA greater than 0.1. This is 0.1 for circular shape. This is 0.1 for hexagonal, for triangle 0.2, for rectangular, for another triangle. This is another triangle for this for square 0.1. See, and the other shapes. So this is the exact for TDA. Okay, this is for TDA greater than or exact. The exact solution. So this is the one that we are looking for. Here is TDA taken from this table. So if the question say you have a circular drainage area, your TDA for pseudo steady state is 0.1. If the question say you have a rectangular shape, see, you can go to this 1.3, rectangular shape of 1, 2, 1, 2. If it is square, you're going to go with 0.1. See, this is what you need to know. Now you will be able to you will be able to get the value for TDA from this plot. Then let me get back to the same topic. Okay. Okay. Mhm. Yes, here. So the first step of MPH, Matthias Bruns Hasbrook, is to get TDA from table 146 for, as you can see, the column of exact for TDA. Now, from the value of TDA, you need to calculate what? You need to calculate this is the starting time in real unit, because TDA PSS, as I said, taken from table 146, this one in dimensionless form. What we need to convert this one to real time parameter, that is TPSS, starting time of or pseudo steady state, using this model. See? Okay, so we got TPSS. Now what we need to compare TPSS, the one we have already calculated here, with our production time. Okay, if the production time is greater than twice the value of TPSS, then what you need? You need to redraw Horner plot using your production time as TPSS instead of TP. When your production time TP greater than twice the value of TPSS, in this case, you need to redraw Horner plot using TPSS instead of TP. But if TB if TB is not greater than twice the value of TBSS, then you do not need to redraw Horner plot. Let me stop at this point again and repeat myself. You're going to calculate TBSS from equation 172. And TBSS, you need TDA taken from table 146. And of course, you have the value of TB, production time. You have already started with TP, that the one that used for Horner plot. So you need to compare the TPSS calculated from equation 172 with your production time used for Horner plot. If the production time is more than 2 TPSS, then redraw Horner plot using TPSS instead of TP. If it's not, then you can use Horner plot as it is. There is no need to redraw Horner plot. Then what will be the step number 3? Step number 3, you're going to calculate what is called dimensionless producing time. Again, you're going to calculate dimensionless producing time. That is TBDA, dimensionless producing time. And this one is calculated from your production time. This is, see, this is TP, dimensionless production time, from equation 174. This is 174. Okay. From TBDA, the dimensionless production time, the one calculated by 174, then we need to go to one of the figures here. Okay, these are 4 figures. See, these are 4 figures. See, let me make them see. So this is your dimensionless production time on the x-axis, dimensionless production time on the x-axis. We have 4 figures here. And you got the value of TBDA, dimensionless time of production time. And you know what is the shape of your reservoir. If you have circular shape, if you have rectangular, if you have square shape. Okay. If it is circular, you can come here. See, this is the circular and hexagonal. See, the first part. See, the first part. See, hexagonal and circular shape, then square, equilateral triangle, see, right triangle. If it is not here, you can come to the second plot here, see, this is rectangular, and here is another rectangular. This is rectangular with the well located close to or in one of the halves. It's not centrally located. Or if you could have something like that. Oh, so, however, it depends on your reservoir configuration and the location of the well bore. Then you have to use the care or the plot here. Then from the value of TBD, for example, from the value of TBDA, the calculated TBDA, okay, then you're going to move, for example, this is your TBDA1, and you have, for example, circular shape. So for circular shape, and you're going to read BDMPH, the dimensionless pressure calculated by Matthias, Bruns, Hasbrook. Dimensionless pressure calculated by Matthias, Bruns, Hasbrook. That is PDMPH. PDMPH. The PDMPH, then you're going to put it here. See, you're going to put it here. And you will be able to calculate average. See, this is the pressure. This is PDMPH. And here's P star. Now, P star is taken from where? P star is taken from Horner plot. When you are going to plot TB plus delta T divided by delta T, and you're going to make the extrapolation to what? Extrapolation to TB plus delta T divided by delta T equal to 1. This is going to give you what? This is going to give you P star. So P star taken from Horner plot minus M divided by 23025 times BDMBH, the one of already estimated from the plots given by Matthias, Bruns, Hasbrook. Then you will be able to calculate average reservoir pressure. See, that's what I said. B star always is less than average reservoir pressure by this value. By this value. B star cannot be equal to P average, but it should be close to P average. So this is the first technique introduced by Matthias, Bruns, Hasbrook. It's called MPH technique. MPH technique. Okay. Now, sometimes if you have what's called a constant pressure square, if you have strong water aquifer, so what we expect to have, we expect that the pressure at the boundary may not be changed. So we could say, okay, we have constant pressure at the boundary. In this case, we need to apply this model, P average equal P star minus M divided by 23025 times the dimensionless pressure calculated by Matthias, Bruns, Hasbrook. Okay. Or you could instead of P average, you could say PE. Sometimes instead of P average, you could say PE or PI, initial reservoir pressure. Okay. So for this case, we're going to go with what? We're going to go with the figure 177. The 177. See, figure 177 going to give you what? Going to give you either the P DMPH or B dash MPH. So either PD MPHE or B dash DMPH. And then you can put them here. See, this is, for example, B dash DMPH, exponential, the term here, or you can put it here. I mean, it's not you are not going to put it here, but this value, see, the first one, if you need to calculate average reservoir pressure, what you need, B dash MBH. But if you need to calculate PE, you need to use PD MPHE. Let me repeat what I have said here. This case for what? For a reservoir with a strong water aquifer. If there is water support that is really very strong, then we are assuming that we have a constant pressure at the reservoir boundary. For this case, we are not going to go with the four plots given by Matthias. Bruns has a brook here. We're going to go with the figure 1.77. So now in TBDA, then you have two lines. You have two lines. One of them going to give you what? Going to give you B dash DMPH. If you know B dash MBH, then you will be able to calculate average reservoir pressure. That is B dash. While the second one going to give you what is called BDMPHE. Then we are going to calculate PE, and P is calculated from this model. Okay. Now, going back, I don't know if you have taken this one in reservoir engineering, but there is some difference between PE and P dash. PE is greater than P dash, but it is less than initial reservoir pressure. What I'm saying? PE is located at a distance more than, I think, more than half the reservoir radius. I'm not sure about the exact equation. Let me check this one, and I will tell you exactly the difference between average, that is P dash, and PE. Why we have PE? Why we have P dash? 1 minute, please. I will tell you that. I'm looking for this topic in my database, and hopefully I will get something to you. Okay. Okay. So, what is the difference between B dash and PE? B dash is B dash, of course. PE is greater than P dash. PE is less than BI. So we have initial reservoir pressure, then we have PE, then we have P dash. Yes, then we have P dash. So PE first, PE second, P dash third. Now, PE is calculated. This is the reservoir pressure calculated at a distance called R. What is R? RE divided by the square root of E. So PE is calculated. This is reservoir pressure, PE, reservoir pressure. When R, this is reservoir pressure, when R equal to RE divided by square root of E. See? And most likely in this case, 1 over square root of E, 1 over square root of E, this is almost greater than, this is almost greater than 0.5. See? While B dash it is also a reservoir pressure calculated where? Calculated at R equal to what? 0.47 RE. See? That is less than half the distance. This is why PE is greater than P dash, but it is less than initial reservoir pressure. So going back to the MPH, Matthias Bruns as a proof, if you have strong aquifer, and if you are going to assume that we could have constant pressure at reservoir boundary, you are going to go with figure 177. Figure 177 going to give you either PDMPH dash or PDMPHE for PE. So whatever you have, you can calculate the P average or PE. If you do not have figure 177, you can calculate PDMPH dash from this model, or you can calculate PDMPHE from this model. This is the analytical solution. So this is Matthias Bruns has a proof. Matthias Bruns has a proof. So let me summarize what we have known so far from the first technique to calculate average reservoir pressure using pressure buildup test by the MPH or Matthias Bruns has proved. So what you need to do, actually, you have to draw your pressure data using Horner plot on semi-log. What you are going to do, you are going to calculate the permeability, the skimp factor, and of course you will be able to calculate what wellbore storage factor. And from Horner plot, you will extrapolate your infinite actin line to the point where TB plus delta T divided by delta T equal to 1, and you're going to calculate B star. What is B star? It is a value close to average reservoir pressure or initial reservoir pressure. This is the first thing. Now what you need to go to table 146 and get the value of TDA PSS, the starting time of pseudo steady state calculated for reservoir drainage area. So from knowing the shape of your reservoir, if it is circular shape or rectangular or square, you're going to go to the table and get the value of TDA PSS. Now from TD, as I say, TDA PSS, this is dimensionless time. What you need to convert TDA for pseudo steady state to real time TPSS using what? Using the model. Here's the model. Which model? 172. Now, when you got TPSS, what you are going to do, you're going to compare TPSS with your production time, the one that you have used in Horner plot, TP. If TB is greater than 2 TPSS, then you need to replot Horner plot using TPSS instead of TP. If it is not, then you're going to keep Horner plot as it is. So you do not need to change. From the production time then, for the production time TP, you have to calculate what? The dimensionless time of producing time. The dimensionless time of production, or the dimensionless production time TBDA from using the equation 174. Now going to the 4 figures here, based on the shape of your reservoir, you can calculate what's called PDMPH. And then put PDMPH here. Now when P star from Horner plot, then you will be able, of course, M, you know M, taken already from the Horner plot. Put PDMPH here, you will be able to calculate P average. So you are done. The only thing that you need to consider, if you have strong water aquifer, if you have good water support, then you can say I have a constant pressure at reservoir boundary. For this case, you're going to go with 177, and 177 going to give you either PDMPH dash or PDMPHE. For both, you can use these 2 models and calculate either P average or PE. If you do not have figure 177, you can use these 2 models, 178 to calculate B dash and BH, or 179, 178, 179 to calculate the P dash, the MPHE, to calculate P. See what I'm saying? So this is MPH. Okay. What I would prefer, actually, in this case, I would prefer to solve an example before going to Dietz method. So let us see if we have example. I'm pretty sure there is example here at the end of. Yeah, this is example 171. I think I do have this one in my database. Yes, exactly, I do have this one. So let me bring this one in front of you so we could work together on it. 171. Yeah, here is 171, 171 exactly, yes. Uh-huh. Mm-hmm. Let me share 171 with you. So guys, this is 171. This is 171. I'm gonna, okay, let me remove all of that. We're gonna start from the beginning as if we do not have all of that. So let me remove because we need to do it by ourselves. See, let me remove all of that, guys. I'm gonna remove this one. So here's what we have. See, we need those. I do not need to do them later. So let me remove all. So this is 171. Here is the data. Let me remove all of that. Okay. So we have RW given to us. We have formation thickness. We have the porosity. We have the viscosity. We have the total compressibility, oil formation volume factor. A Q, the flow rate is given to us. And it is we know that PWF at the moment of the shut-in also, this is when delta T equal to 0. We have the cumulative production. And we got the area given to us, acres. See? The area given to us, acres. Okay. Now, as you know, to plot Horner, I mean to go with Horner plot, we need to know how much our production time, and it is not given to us. Our production time is not given, but we can calculate the production time from the cumulative production divided by the flow rate, and this would be in what? This would be in days, and we know that TD or the time should be in hours. So what we're going to do, we're going to multiply by 24 so we could have it in hours. See, now here is your TP in hours. Now we're going to calculate using Horner plot, that is TP, production time, plus DT divided by DT. This is Horner plot. So this is your production time, F4 plus DT. This is your DT. See, divided by what? Divided by dt again. See, and you are done. So we're gonna move down all the way down. See, so this is our dt. Now we are gonna plot remove all the old data here. This is the new plot we need. Okay, so what you need now, select data, add x-axis. This is your x-axis, see guys, and here is your pressure. Good. And as you know, we're going to go with semi-log plot. So x-axis should be in logarithmic scale. And this is what you have. See? Now let me rearrange this one, make it bigger, so you could see that clearly. And I'm going to do the same for y-axis for the pressure. Okay. And we can make the things here, the not the the markers, make them more clear. See, markers, marker option built in. So make them, for example, 8 or 9. Okay, good. So they are clear now. And the other thing, we do have the, let me see the grid lines. I need to make them clear. So this would be like this. So good. And we need to have the grid lines, the minor and see minor also, so we could recognize them. Grid line, this is black also, good. And now I'm going to go with the minor a little bit. See, we can see them now. Another one. Okay, So this is what we have. Let me put the X titles, guys, the X titles here. So this is what? TP plus DT divided by DT. And I'm going to make them a little bit big, see? And this is, of course, what? This is BWS, as you know. This is PSI. So right now we have everything is ready. See? Again, where is your infinite actin line? As I said many times, please be careful from early production time. Early production time, we would not like to use the pressure data taken from early production time, because this part of data is controlled by wellbore storage effect. So what we need to take more than 10 hours. Where is that? Let me see. So this is the part that we are looking for. See, this is what we need to look for, not that part. See, I think this one is good now. See, this one is good. Okay, and let me make it red. Big. See, and we are good now. Now we need to have the extrapolation to 1. So I guess this one should be, let me see, to put it until 4,000. So we can estimate this one very well. 4,000. Okay. And it should not be 0, actually. 0 is not the one. So let me say 2,000. See. $3,000. Actually, let me try 3,000 more. Okay, and not 4,000, less than 4,000. Let me see. This should be the maximum. 3.8. Okay, good. 3.6. Let me see. I think 3.6 is good now. And this is our line. See, this is our line here. So this is our line. As you know, we need to calculate what? We need to calculate M, and M is what? The slope. So the slope in this case will be what? Will be, let me see, for 100, it is 3,320. So, or let me start from 10. So 3,308 minus 3,020. So this is our slope. And then we're going to go and calculate the permeability. That is what? The permeability is 162.6 times Q, the mu, oil formation volume factor, divided by what? Divided by the slope, this one, times what? Times H. So this is your permeability, guys. So this is millidarcy. Now you can calculate, basically you can calculate skin factor, and you can calculate wellbore storage. We are not going to go, but it is required to calculate skin factor. And okay, let us do it now. BWS, we are going to go with, let me bring, of course, the models. So where is the models? We do not have them. Okay. Let me bring them in front of you, the models for, are they calculated here? Of course, K is calculated. So here is, yeah, here is the skin factor. So snip, okay. New. So this is the model for skin factor, for example. Guys, this is the model for skin factor. So we're going to use this one to calculate a skin factor. But what we need, We need to know P1 hour, PWS 1 hour. See? And this one is what? This one is, we can read it from the infinite actin line for 1 hour. So this would be what? This would be TB plus delta T divided by delta T. TB plus delta T divided by delta T. So this would be TP, that is 321 plus 1 divided by 1. So 322. 322. Where we are? We are here. This is 100, 200, 3. So insert. This is a 320 somewhere here. And we are going to read the pressure. We're going to read the pressure. So the pressure is close to what? 3,000. So 3,000. This would be 3,290. This is PSI. See? PSI. So we're going to put it here and we are going to calculate. C, that is 1.151 times what? Times the pressure 1 hour minus the pressure at the moment of the shutting. It is given to us, this one, divided by what? Divided by the slope here, minus log of what? Log K, okay? Divided by what? Phi mu CT, phi mu somewhere CT RW square close plus 3.23 and close the big parenthesis, and this is your skin factor. For well bore storage, we know how to do it for well bore storage, but we need to plot what? Delta P versus delta T on log plot. We're not going to do it here. I'm going to leave it to you. So the most important thing that you need to do here is to calculate what? Is to calculate the permeability, and this is the permeability, and P star, because you need for P star. So P star is taken from where? P star is taken from delta T, that is equal to infinity. See, delta T, that is equal to infinity. So delta T equal to infinity, TB plus infinity divided by infinity, this would be 1. So P star is taken from where? P star is taken from this point here. See, this is your P star. See, this is your P star. How much your P star? It is 3,440. 3,440 PSI. This is your P star. Now you are done with Horner plot. What you need to do, you need to get TD PSS. TD PSS taken from table 146. But what you need to know, you need to know the shape of your reservoir. The question said, okay, let me see. The question say that the reservoir is circular, square drainage area. Square drainage area, not circular, square drainage area. So we're going to go to table 146 and look for square drainage area. I think slide page 15, 115, I think, somewhere. Table 146, I think 146. We are looking for it. Okay, we will read this one. Yeah, here it is. So for square, so TD A PSS is 0.1. See, this is 0.1. This is square. See, guys, this is square here, square. So it is 0.1 taken from exact for TDA greater than, exact for TDA greater than what? Greater than 0.1. This is square, so this is the value that we are looking for. And now we're going to get back. Yes. Yes, here is the topic. Okay. So now TDPA, TDA PSS, this would be what? 0.1. Okay. Now what you need? You need to calculate you need to convert this one to PSS using this model. So TPSS using this model, what would be? Porosity, see, phi mu CTA, phi mu CTA, phi mu CT, A, here is A, divided by what? 0.0002637 times K. This is K already calculated. See? Times what? Times TD PSS. This is TD PSS. This should be what? This should be hours. This should be hours. One thing that we need to consider when we are going to use when we need to calculate TP SS in this case, we have to convert the area, I mean reservoir area, from acres to feet. So we have the area, like, see, the area is 40. This is A3. This should be multiplied by 43,560 just to change acres to feet. So basically, the TPSS is 110 hours. 110 hours. Now, we are going to make the comparison between what? Between TP, how much our TP? So TP, as you know, guys, TP is what? TP is calculated to be what? TP is calculated to be, this is TP. See? So TP is greater than 2 times TPSS. So in this case, we have to redraw Horner plot. And this time we are going to use this one instead of production time. So what we are going to do, we're going to say TPSS plus dt divided by dt. So what I'm saying? And we're going to use TPSS. This is TPSS, see? Plus, of course, this is constant, plus dt, this is dt, divided by dt. See, guys? And this should be not for the pressure, this should be for time, actually. So this is your time. See? So now we are going to what? We are going to re-plot Horner again, and I'm gonna put it here. This is your scan factor. So I'm gonna use the same, but instead of using, this is Horner plot using TP, I'm gonna move to this one. There will be very little change. See, very little change. So what we will see, we're gonna draw this one down. The slope will be the same. The slope will be the same, but P star is not going to be the same. P star, see, now P star is what? 3,418. So P star now, see, P star now is what? P star is 3,418 PSI. It was 3,440. See, this is the difference. The slope will be the same. There will be no change in your slope, except that your P star will be less. Okay? Now what we are going to do, we are going to calculate what? We are going to calculate TBDA. Where is the model for TBDA? This is TBDA. See, TBDA. So what is TBDA? TPDA. We're going to calculate TBDA using what? 0.000267 times K. K, as I said, it is not going to change. Times TP, and TP in this case will be what? TPSS. See? Divided by phi mu CTA. Phi mu CTA times what? 43560, and you are done. So this is your TBDA. So what I'm saying, this is your TBDA. So it is 0.1. Now we're going to go to the 4 figures given by Matthias Prunes, and we are going to use the first one. The first one for what? Either, as you know, guys, either for hexagonal, circle, the first one, and the one just below is for a square. So the first one. So let me do it from the. Okay, I think I can do it here. So this is the one. See, here is the line. The second one. See, square. Here is square. So what you need to do, you need to move from 0.1. This is 0.1. See, this is 0.1 here, 0.1. See, from 0.1 here, and move to the almost to the first curve, and get it read. Get it read from this one. See. So how much? Almost 1.2. So BDMPH almost 1.2. 1.2. Almost 1.2. So in this case, PDMPH almost 1.2. Now you can calculate P average. This is P average. See, P average. So P average is what? B average. This is B dash. Always sometimes it's written P average. B star. This is B star minus the slope. Same. It's not going to change. See, divided by 2.303 times what? PDMPH. And this is your P average. See, this is your P average. Is that clear? I think yes. So it is almost 3,386. 3,386. We are close to where? We are close here. 3,000. See, almost here. Here. This is 90. Okay. So here is the way to calculate average reservoir pressure using Matthias Prunes Hasbrouck. Matthias Prunes Hasbrouck. In the textbook, the average pressure is calculated to be 3,376. For our case, it is 3,386. 86. Okay, this would be fine. So this is the way to how to calculate average reservoir pressure using the MPH technique or the Matthias Prunes Hasbrouck. Matthias Prunes Hasbrouck. Now we're going to go to the second technique. The second technique is the Dice method. Now, let me now share with you. Okay. So this is Dice method. Now the second technique to calculate average reservoir pressure using pressure buildup test is Dice method. Now, using this technique, we need to know first of all, we need to know the reservoir shape. If we know the reservoir shape, we can estimate the value of the shape factor. So if we know that the reservoir is circular drainage area, we can go to table 146 and get the value of shape factor, C sub A. Now, when you know the shape factor, then you will be able to what? You will be able to calculate delta TB dash. See, Delta TB dash is calculated from this model 179. And see, this is your shape factor, and this is your drainage area. See, guys? So Dyke's method says that you have to know the reservoir configuration. Now, in the reservoir configuration, you can estimate from table 146 the shape factor. Now, in the area, now in the shape factor, you will be able to calculate what's called delta TB dash. Now, if you do not know the reservoir configuration and you do not know the shape factor, then you can calculate delta TB dash from this model. See, if you do not know your reservoir configuration, you are not sure about your reservoir configuration, and if you do not know the shape factor, okay, sometimes the reservoir configuration, it's not a circle, it's not a square, it's not a rectangle, something else, then you cannot find the shape factor from the table 146. So what you have to do, you need to calculate delta TB dash from this model, model 1719. 0.002637K, 5 UCTRW, delta TDAB dash, and delta TDAB dash is calculated by this model. See? Okay. So, if you know your reservoir configuration, then you will be able to get CA from table 146. If you do not know your reservoir configuration, if you are not sure about your reservoir configuration, you can calculate delta TB dash. But before that, you need to calculate delta TDAB dash. And what you need TBDA. What is TBDA? This is dimensionless production time. And you know how to calculate dimensionless production time from the model already given to you based on production time TP. 0.002637 KTP divided by 5 UCTRW. Then you are going to go with plot your delta T, not Horner plot this time, not delta T, delta TE, not Horner plot, not delta TE. You're going to plot delta T versus pressure on semi-log plot. Delta T as it is versus PWS. When you plot your pressure versus delta T on semi-log plot, you are going to use the value of delta TB dash. See, the value of delta TB dash, you're going to use it. Go to the infinite actin line and read the value of the pressure directly. Read the value of the pressure directly. And this is your average reservoir pressure, no more. This is Dyke's method. So let me repeat the procedures for Dyke's method. Dyke's method says that you need to know what? You need to know your reservoir configuration. If you know your reservoir configuration, either circular shape, square, rectangular, hexagonal, then you can go to table 146 and get the value of shape factor. Sometimes you do not know the shape of your reservoir. You do not know your reservoir configuration, or you are not sure about your reservoir configuration. Then in this case, you have to calculate delta TB dash using the model 1719. For the model 1719, you need to know delta TDAB dash, and this would be calculated by the model 1720. For the model 1720, you need the dimensionless production time, and we know how to calculate dimensionless production time. TBDA is 0.002637 KTP divided by 5 UCT RW square. You are done with this one, then you're going to go with the plot of your pressure versus delta T. See, delta T as it is delta T on semi-log plot. When you got this plot, then you can use delta TB dash directly with the infinite actin line. You will be able to estimate your average reservoir pressure. This is Dyke's method, guys. So now I'm going to go to the same example already solved before for Matthias Brons Hasbro and see how much Dyke's going to give me. Same, where is that example? Okay, 171. This is 171, okay. So I'm going to solve this one for what? For Dyke's. See? So what I'm going to do, I'm going to move all the data here. So this is, this is sheet number 1. I'm going to rename it, say this is MPH, so we could recognize it, MPH. And now I'm going to open a new sheet, copy, a new sheet, and the new sheet I'm going to call it dice. Okay, let me put this one here. Okay, this is the data given to us. Here is the data. There is something wrong here. Let me see. Okay, let me get back. Okay. Okay. So this is what we have, and I'm gonna copy the pressure data. See, taken from this sheet, put it here. Okay. So this is what we have, guys. So now for this question, we know the shape of the drainage area. It is square drainage area. So basically, we're going to go to the same table and see how much is the shape factor for square drainage area. So we're going to go, I'm not going to share it with you. I'm going to do it by myself. So I'm going to go to table 146 again. Look for the shape factor. See, where is that? Shape factor. Yeah, here is shape factor, slide number 90, the shape factor for square 308828. The shape factor of the square 30, so CA, this would be 308828. This is from table 146. This is from table 146. Okay. I'm just waiting a little bit. See. Okay. Okay. So this is yes. Okay. So this is our shape factor 3308828 taken from where? Table 146, slide number 90. And then what we need to calculate what? We need to calculate the delta TP dash using the model. Delta TP dash, let me get back so I could bring delta TP dash in front of you. Mhm. Okay, where is delta TP dash? Here's. So this is delta TB dash. This is the model for delta TB dash. Now we're going to calculate DTB dash. See? Okay, should be something like that. Okay. So this would be what? This would be phi mu CT. Area should be changed to fit, so it is times 43560 divided by what? 0.0002637 times CA. This is CA, and K in this case. Okay, we have to calculate K in this case. So let me say that K is this one here. Okay, I'm gonna close it. See. This is K. So what we need the value of K. Now, how can we calculate the value of K? As I said, Diet's method says that you have to plot delta T versus delta T. Delta T versus pressure. So delta T as it is delta T. Not Horner plot, not delta T. So I'm going to go with insert, insert this one. Okay. See. And select data. Add. See. This is your delta T as it is. See. And this is your pressure. See. Okay. And this should be log scale, logarithmic scale. This would be fine. See, guys. Now, kind of organize the chart, your chart. So let me get it down a little bit. And this one would be, okay. This one also. So, and I'm going to change the markers, make them bigger. Okay. Now we need to add the grid lines. The grid lines all should be clear. So basically, I'm gonna go with the major grid line, change them to black. Okay, good. And the minor grid line, I'm going to change them to black. The major grid line also, change them. Now I'm going to go to the minor and put them like this. And we do have the x-axis minor. And now we are good. See? Now we are good. So we can see. Now we are going to look for the straight line, for the infinite actin line. Where is that? This is our infinite actin line. See, guys, here, somewhere here. See, this is our infinite actin line. I will make it bigger. Red color. Red color. So this is what we have. As much as we can get more points included, I think we are good now. So we are good now. See? So how much the slope in this case? How much the slope? So because we need the slope to calculate what? To calculate the permeability, of course. So the slope is what? M. Let me put it here. So M is 3,350, 3350 minus 3310. This is almost 40. See, 40. Then K is what? 1626. 1626 times what? Times Q mu oil formation volume factor divided by the slope here divided by H, the formation thickness, and you will be, this is your millidarcy. See, this is your millidarcy. And this is very typical. You do not expect that the permeability calculated by Dietz will be the same for the permeability calculated by Horner plot. There should be some difference between them. So now we got having the permeability in our hand. The delta TPE dash is given to us like 23.73 hours. Okay. So from the same plot using this value, see, now we're gonna go with this one. So 23.72, where is that? 10, 20, so 23 almost here. Going to the infinite actin line and reading the pressure. In this case, the pressure is 3,350, 12. So B average in this case by Dietz is 3, 3, 5, 3, 3, 5. Oh, sorry, let me, I think 3, 3, 50. Yes, this is 60. 3, 3, 62 psi. See? While the one calculated by MPH, 3386. Now 3362. Less. This is Dietz. Okay? Here is Dietz. The one already calculated in my notes using Dietz. Let me see how much. I don't know if it is calculated here. Yes, Dietz is calculated. So 3368, while mine is 3362. Okay. Now we're going to go to the third technique. The third technique is Ramy-Cobb method. So let me share with you my slides again, so I could explain Ramy-Cobb. Here is Ramy-Cobb method, guys. This is Ramy-Cobb method. Now for Ramy-Cobb method, we're going to go again. We're going to go with Horner plot. TP plus delta T divided by delta T. This is Horner plot. Now, we need to calculate, of course, the production time. You cannot do Horner plot without knowing TP. So this is very typical. And you need to calculate TPSS, the starting time of a pseudo steady state. Okay. Now, if TB is more than TPSS, if production time more than TPSS, then calculate what is called the time ratio, TB plus delta T divided by delta T, P average. And this one is calculated at what? This one is calculated at TP. So what you need, guys, again, you need to calculate how, of course, you will be able to know how much your production time, either if it is given to you or calculated from the cumulative production divided by the flow rate. So you know how much TB. Now, what you need from Horner plot, you can estimate your TPSS. Or you can go to table 146 based on the reservoir configuration. You can calculate TDA PSS and then convert TDA PSS to 2PSS. Compare TB with 2TPSS. If TB is more than TBSS, if TB production time more than TBSS, then you need to calculate the time ratio at the P average using what? Using the model 1711. And at this time, what you need to put? You need to put production time TP. See? You need to know the shape factor. If you know the reservoir configuration, you can go to table 146 and get the shape factor. If you do not know your shape factor, if you are not sure about your shape factor, then you may need to calculate TB plus delta T, or the time ratio, using this model. This one for the case if you do not know the reservoir configuration, if you do not know your shape factor, so the time ratio can be calculated from this model. See? So what we have here, we have TBDA, 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 TBDA. What is TBDA? Dimensionless production time, calculated based on what? Based on your production time TP. This model is used if you do not know your shape factor. If you know your shape factor, of course, you can go and get the shape factor, put it here, and this is area, and use TP. See? So you have two options. Okay? Okay. Now we are going to go with Horner plot and get the value of the permeability, of course. At the beginning, you need to calculate the value of the permeability. And from Horner plot, using the time ratio here, TB plus delta T, at delta T for average reservoir pressure, you're going to go to the infinite actin line and get the value of average pressure. And this would be done. Ramy-Cobb method. Let me repeat what we need to do with Ramy-Cobb method. Ramy-Cobb method, you have to use Horner plot. Horner plot TB plus delta T divided by delta T with PWS. So you have to know how much your TP. Now, if you know your reservoir configuration, then you know your shape factor, then this would be fine. Okay? You have two options in this case. The first option, if you know your reservoir configuration, if you know shape factor, this would be fine. Then what you need? You need to compare TP versus TPSS. And TPSS almost is taken from where? From table 146, TDAPSS, and convert TDAPSS to PSS. That's what I said. You have to know what is the reservoir configuration. And then you know your CA, you know your TP, you know your area. Then you are going to calculate TB delta T divided by delta T at average reservoir pressure using the model 171. Now, if you do not know your reservoir configuration or you are not sure about your reservoir configuration, then you can go with this model to calculate the time ratio that you need to use for average reservoir pressure. And for this value, this model here, 1721, you need what? You need only TBDA. What is TBDA? Dimensionless production time. Dimensionless production time calculated at production time, TP. Which one you are going to have in your hand? You're going to go to Horner plot and go into the infinite actant line, and you will be able to calculate average reservoir pressure. That is all. See? So now let us go to the same example, and let us work together with Ramy-Cobb method. So let me share the Excel sheet with you again. This is the one, okay? And let me move the data that we need for, before that, let me open a new one, say Ramy-Cobb, name it Ramy-Cobb, Ramy-Cobb. This is Ramy-Cobb, okay. Okay, and now, okay, I am going to copy the data to this one, see, okay, good. Uh-huh. Okay. Okay. So here is what we have. Now I'm gonna bring the data for the pressure. So this is your pressure data. Going to Ramy-Cobb. Now what you need, as I said, for Ramy-Cobb, you have to do by Horner plot. So TB plus delta T divided by delta T. Let me increase the font here so we could see that clearly. So this would be, this is TP constant plus DT, see, divided by DT, and this would be see, and now we are gonna plot this one. This is very typical, guys. So this is Horner plot. Remove the old data. Okay. Make it bigger. Okay. Select data. Okay. This is your time. And here is your pressure. And this would be what? This would be logarithmic scale. Good. Now we will make it nice. So reorganize everything. So this is bigger, okay. And we are going to do for the Y. Okay. So this would be nice. And for the markers, we are going to do the same. Okay. Now we need to work with the grid lines, the major and minor grid lines. The major plaque, the major black again. Now light blue, again light blue. So we are good now, and we are gonna increase this one to 4360. So we would see, okay, 360. Okay, good, good, good. So, and now I am going to plot the line going through the infinite actin line. This is our infinite actin line, guys. Okay, and we are going to go here to P star, make it clear. Red color. Good. So this is our line. And this is very typical, you know, guys. We're going to go with M. The slope in this case is what? Is 344 minus 3, no, sorry, 3380. I think, yes. 3310, 80 minus 3310 or 20 or even more probably, yeah, something like that. And K will be calculated here as 162.6 times Q nu B, Q mu oil formation volume factor divided by the slope here times formation thickness. This would be millidarcy. I think the same that we got it for MPH. So we got the permeability. Now, do we know the reservoir configuration? Yes, the question says it's a square. So what we need to get shape factor. We need to get the TPSS. So we're going to go to table 146 again, and we will have these two values. What are they? T, D, A. And we know this one is 0.1. And we need the shape factor for this one. And we know the shape factor is what? 38.828. Already taken from table 146. So we know that. From where these two things? From table 146, slide number 90. So since we know that, what we're gonna calculate the time rate given by Rami Cobb. This is the time rate. See, I'm gonna bring this one in front of you so you can see that. So what we are gonna do, we're gonna calculate the time rate. This is the time rate. See, guys, this is the model. So what we need to calculate TP. See, guys, TP plus dt divided by dt, all at average reservoir pressure. So this would be how much? Let us see. This would be 0.002637 times K, already calculated here, times what? CA. This is CA. Divided by what? Phi mu CT, phi mu CT times A. This is A, and be careful, you should be for 43,560, and then all times what? Times your production time. That is your production time. And you have to know that your production time, before that, you need to know that your production time is greater than what? TPSS. So TPSS is calculated by what? Let me remove this one down, put it here. Now we need to know how much TPSS. So TPSS is calculated by what? It's calculated by this model. Let me bring the model in front of you so you would know how TPSS is calculated. I think we do have a TPSS somewhere. Yeah, this is TPSS. So this is TPSS, guys. I'm going to put it here. So let me put this one here and TPSS here. So, right. So TPSS is what? Phi. This is phi mu. This is a mu. CT. This is CT times A, this is A, again, times 43560 divided by what? 0.0002637 times K, this is K, times what? TDPSS, this one. See? So it is 110 almost, while your production time is 321. So basically, your production time is more than TPSS. This is why you have to use this model here. So now you got 9. Now, from the Horner plot, using 9, that is here, see, here, somewhere here, see, this is 9. Go to the infinite actin line, go to the infinite actin line, and read the pressure. How much? 3380. So P average in this case, P average is what? 3380 psi. See? 3380 psi. This is Ramy-Cobb method. This is Ramy-Cobb method. So now we have covered what? We have covered MPH, Matthias Bruns Hasbro. We have covered Dietz method. We have covered Ramy-Cobb. Now we're going to go to the last one, the fourth one, that is the MDH or Miller-Dietz Hutchinson. So let me share with you my notes again so we could finish. Okay. Share this one with you. So this is Miller-Dietz Hutchinson. Miller-Dietz Hutchinson. Now for Miller-Dietz, you know guys, Miller-Dietz, we have taken Miller-Dietz Hutchinson. Miller-Dietz Hutchinson is to plot delta T versus PWS. Delta T as it is delta T. We do not consider how much the production time. We just use delta T. So basically, we're going to go with the MDH plot. MDH plot, delta T versus PWS on semi-log plot, and we're going to calculate the permeability, of course. Okay. Now, using the same plot, the MDH, pick any point for the time. Any point for the time, and read the value of the pressure. See? So let me say that the any point of the time will be Tn, and the pressure will be BWSN. Now, for the time point that you're going to use, calculate what's called delta TDA. Use what? The point of the time that you're going to pick it from the plot. See? 0.000263.7K, 5 mu CTA, delta Tn, the time point that you're going to use. Okay? So you got delta TDA. Now, delta TDA will be used with figure 178 here, figure 178. See, this is figure 178. And read what's called BDMPH based on what reservoir configuration. The first line at the top, this is for closed reservoirs. See, closed reservoirs, either square or circle. While the second one, this is for what? This is for the constant pressure reservoirs when you have some water support. So the first one for closed reservoirs or closed systems, the second one for constant pressure systems, as if we have a strong water aquifer or strong water support. So based on the case that you have, you're going to use delta TDA calculated by 1712, go to this line and get the value of PDMDH. Then P average, the value of the pressure for the time point that you have used, plus the slope divided by 1.15 times BDMDH. This is your average reservoir pressure. If you're going to work with the second line, if you have water support, then you have to use the model 1714. The model 1714. Okay? This is MDH. So MDH, let me repeat what I have said for MDH. MDH, we're going to go with MDH plot. MDH plot, you're going to plot delta T as it is versus PWS. And then when you got your plot, pick any time point. Go to the infinite actin line, read the pressure. So what you have? Delta Tn, BWSN. Delta Tn, BWSN. Then for delta Tn, calculate the dimensionless time. That is delta TDA, using the model 1712. Now, from delta TA, the calculated delta TA, you can use to figure 178 based on the condition of the reservoir. If you have closed reservoir, circular or square, and get the value of PD and pH read. If you have strong water aquifer, you are going to use the second one, the lower one. Now, the value that you are going to have it from 178 would be used either in equation 1713 closed system or 1714 for water support to calculate what? P average. But you need to use what? The value of the pressure order taken from MDH plot. This would be very clear when we're going to apply the MDH for the same example here. So I'm going to get back to the example and share it with you. Okay, this is the example. So I'm going to open a new. This is, let me call it MDH. Rename MDH. See? And now I'm going to bring the same thing. So same data, guys. Okay. Copy. Put them here. Okay. Okay. So here's what we have. Okay. Good. And now I'm going to bring the pressure data. See, this is our pressure data, guys. Okay. Okay. So this is Miller Dice Hutchinson. So we're going to plot directly delta T with the PWS. So this is delta T, as you can see. And of course, PWS. And guys, we know that this is logarithmic scale, so I mean, good. Now we're gonna organize our plot. So this is what we have, and we are gonna make them bigger. So this would be like this, and this would be like this, okay? And I'm going to increase the mark options here. Okay, good. Now I'm going to set the grid lines. Grid lines, guys, see, grid lines. And for the major grid lines, we're going to go with black. For minor, a little bit light blue. See, this is what we have. And the things that we are going to go with our slope, see how much we could read the slope in this case. Make it red. So the slope in this case, let me see M. How much M in this case? M is going to be 3350 minus 3310. This is the slope. See? And now we're going to calculate the permeability. This is very typical. I mean, times Q nu B, Q mu oil formation volume factor divided by slope times formation thickness, and you are done. This is your permeability in millidarcy. Now the procedure says you need to pick any time point. You need to pick any time point here. So let me say that we are going to pick what? Any time point. So we're going to pick what? 10, for example. So your time point is 10. You're going to go to the infinite actin line and 3350. So Tn is what? Or dTn. This is 10. See? And of course 10 hours. And dBWSN, the one that we are going to read it from here, 3350 PSI. Good. Now we are going to calculate what? Let me bring the model in front of you. You are going to calculate delta TDA for the time point. This is the model. Here is the model. So dTDA, guys, okay. This would be what? 0.0002637 times K. This is K. Times what? Delta TDN. This is delta TDN. Divided by phi mu CTA. Phi mu CTA, and this would be 43560 close, and you are done. So this is DTA. Now you are going to go to the plot given by Miller-Dice Hutchinson, and let me bring this plot in front of you so you could see that. This is the plot given by Miller-Dice Hutchinson. See how much now delta TDE? 0.0. It's not clear here, but let me see. It should be okay. Let me make it bigger in my plot. So this is 104. So guys, this cycle is 0.0001, and this one is 0.001. This one is 0.01. So we are here. 0.01, we are here. Close. See? So we are here. Here. So we're going to plot this one. 0.01 here. So 013. And we have, of course, a closed system. So we're going to move up to this point and read the pressure. That is 2. See, this is 0, 1, 2, 3, 4, 5. Be careful. 0 at the top, 5 at the bottom. So 0, 1, 2. So we are close to what? Less than 1. Less than 1. So we are 0, 0.2, 0.4, 0.6. So PD MDH is 0.6. 0.6. See? Now when we have this one, we can go to the model. I'm going to bring the model in front of you again and get the average pressure. See? This is the value for average pressure. See? So P average is PWSN, this one, plus the slope divided by 151, see 3, 1513 times what? MDH. So this is a 3371 PSI. See? So for the first one, from MPH, Matthias Bruce we got 3386. Dites, we got 3362. And we got from Ranico 338. From Miller Dice 3371 almost. Okay. These are the main 4 techniques to calculate average reservoir pressure. And of course, guys, as I told you before, we may have also 2, but they are not important. The first one is external pressure method, while the second one is the direct method. From the external pressure method, we're going to use with this plot, to get the value of what's called BD dash, and then use this model 1715. Or we could go with the analytical solution given to us by equation 1716 or 1717. While for direct method, you just need to use this model 1718. However, I do not trust the external pressure method, direct method. I would prefer always to use one of the four methods. Okay, so this is example 171, the one that has been solved now using the four uh, techniques. Now we have reached to the last item in chapter 1. I have finished chapter 1. So almost we have covered most of the topics given to us in chapter 1. Hopefully next week we are going to start with chapter 2. Now guys, since this week and last week you have not been with me, what you need to read the records, read them carefully. So I don't mind if next week we will have it for the discussion only after the exam. Discuss and the questions about this week, the records of this week and the records of the last week. We do not need to move ahead to chapter 2 and leaving something behind. I need you, all of you guys, after the exam to read or to listen very carefully to the records of the last week and the records of this week. And if there is something missing, if there is something that you couldn't catch it, you couldn't understand, next week you may ask me. So next week we could have it for all the discussions of the topics covered this week and the week before. If everything is clear to you, then we're going to go to chapter 2. Okay, so thank you so much, guys, and hope to see you next week.